Higher order derivatives. Up till now, we've looked at the first derivative of a function. But if a function has a derivative that is differentiable, meaning you can differentiate its derivative, then its second derivative is the derivative of the derivative. As far as notation is concerned, second derivative, we put two tick marks next to the f to indicate a second derivative, but there are other notations. This notation reads the derivative with respect to x of the derivative of f. This notation reads the second derivative of f with respect to x. And if your function is written in terms of y, this derivative reads the second derivative of y with respect to x. Let's look at an example. F of x is equal to x to the fourth plus 1 over x. We want to take a derivative, so we will differentiate x to the fourth and get 4x cubed, and 1 over x and get negative 1 over x squared. And when we differentiate a second time, we take the derivative of 4x cubed and get 12x squared, and the derivative of negative 1 over x squared and get plus 2 over x cubed, and so on if we were going to continue differentiating. But before we continue differentiating, let us put a spin on this in terms of a position function. If t is time in hours, and the position of a vehicle at a certain time t is given by the function s of t is equal to t squared plus 5t, where s is in terms of how many miles have gone by after t hours, then the first derivative is going to represent the vehicle's velocity. And if we differentiate t squared plus 5t, we end up with 2t plus 5. The units, miles per t, miles per hour. And if we differentiate the velocity function, we get the acceleration function, the second derivative of the position function. Well, we would differentiate 2t plus 5 and get 2. The units, miles per hour, per hour. Next, turn our attention to derivatives of a higher order than 2. In other words, a first derivative is considered a derivative of order 1, and a second derivative is a derivative of order 2. Third derivative is the derivative of the second derivative. Third derivative of f with respect to x, if you will. A fourth derivative is the derivative of the third derivative. Derivative of f with respect to x, you differentiate that, you get a second derivative. Differentiate it again, you get a third derivative. We're looking at a fourth derivative down the line. The fifth derivative is the derivative of the fourth derivative. Read the fifth derivative of f with respect to x. And so if we pause long enough to say that for any value n, the nth derivative of f is the derivative of the n minus 1 order derivative. Now let's look at the notation dn f of dx. For an example that will go very quickly, we'll consider a function g of x equaling e to the 3x plus 1. This is going to be a function that if we were going to choose to differentiate, it's in the form of e to the u. We have a chain rule. The derivative is e to the u times u prime. So the first derivative would be e to the 3x plus 1 times the derivative of 3x plus 1, which is 3. Now notice each successive derivative will have a constant times e to the 3x plus 1. Each successive derivative will be the chain rule, e to the 3x plus 1 times 3, times whatever constant you have in front. So watch as we unfold the second derivative, 3 squared e to the 3x plus 1. The third derivative, 3 cubed e to the 3x plus 1. The fourth derivative, 3 to the fourth times e to the 3x plus 1. And arbitrarily, the fifth derivative, 3 to the 5th e to the 3x plus 1. What does this mean? Well, if we want to find the nth order derivative of g of x, it would be 3 to the n times e to the 3x plus 1. Let's put a geometric interpretation onto the second derivative. First of all, just some terminology. A curve is considered concave up where the slope is increasing as you read from left to right. So, if we go ahead and sketch a curve that's concave up, what we're referring to is a curve that has maybe a negative slope, and as I move to the right it has a slope of 0, and as I move to the right further it now has a positive slope. As I move from left to right, the slope is increasing. We say this means the second derivative is positive because the rate of change of the slope is represented as a positive value since the function itself, which is the derivative, is increasing. Similarly, a curve is concave down where its slope is decreasing. General shape looks like an upside down U. Slope is decreasing refers to the fact as you move from left to right, the slope of the curve decreases. Here's a positive slope. Move to the right, here's a slope of 0. Move to the right further, here's a slope of some negative number. So that means that the first derivative is a function that is decreasing. The second derivative, therefore, is negative. Now, a point of inflection occurs at a point in the domain of f where the graph changes concavity. In other words, this means the graph changes from concave up to concave down, or from concave down to concave up at the point of inflection. Here's a visual. If you notice, we have a curve, and the point of inflection you see in brown. Left of the point of inflection, the curve is concave up. Right of the point of inflection, the curve is concave down. Left of the point of inflection, the second derivative is positive. Right of the point of inflection, the second derivative is negative. An easy acronym to keep this straight in your mind is CUP. Concave up refers to the second derivative being positive. Easy enough rubric to remember. Say CUP 3-4 times and you have it for life. Concave up, positive. Therefore, concave down refers to a second derivative that is negative. We can use the second derivative test to be able to extrapolate where we have extrema. This graph you see has 2 points marked along the x-axis, one at C and one at D. Notice, at C we have relative extrema. At D we have relative extrema. The goal is to use the second derivative to determine if the relative extrema at C is a maximum or minimum, and the relative extrema at D is a maximum or minimum. Now, you know the answer by looking at the graph, but let us think about this second derivative test. And it says a relative maximum occurs at x equals c if at x equals c there is a stationary point, and the second derivative is negative. Now think about this. If the second derivative is negative, concave down, negative, you have an upside down u. If you know you have a stationary point at C, that means you have a horizontal tangent. Where's the only spot to have a horizontal tangent on that shape? That would occur at our relative maximum. You can probably look ahead and decide what we're going to talk about next, right? But that means that the second derivative evaluated at C is negative. Relative minimum. Let's turn to a relative minimum. Relative minimum occurs at x equals D if at x equals d there is a stationary point and the second derivative is positive. Now, let's think this through for a moment. Second derivative is positive, so the general shape is concave up, positive, U-shaped. Because at x equals d we have a stationary point, we know we have a horizontal tangent. Where's the only spot along that curve where you would have a horizontal tangent? At a relative minima. Now you know what I'm going to say, right? This means the second derivative evaluated at d is going to be positive. So for relative maximum, the second derivative is negative, and for a relative minimum, the second derivative is positive. Let's determine stationary points, points of inflection, local, and locations of the relative maximum and minima using a second derivative test. First step, take the first derivative. Derivative of x cubed is 3x squared, derivative of minus 6x squared is minus 12x, and the derivative of this constant 15 is 0. Now I'm looking for stationary points, so I'll set the first derivative equal to 0. And at the same time, I'll factor out 3x from both terms. That gives me 3x times x minus 4. Solving, I find x equals 0 or x equals 4. So at these locations, we have a stationary point, since these points are in the domain. Now let's take a second derivative. Derivative of 3x squared is 6x. The derivative of negative 12x is negative 12. And if we set the derivative equal to 0 and solve, we have a possible inflection point. We'll come back to the word possible in a moment. We solve this equation that's set equal to 0 by factoring out a 6 from both terms, and setting x minus 2 equal to 0, we find x to be 2. Now x equals 2 is in the domain of the function. It is where the second derivative is 0. But this is not an inflection point with certainty. It is a possible inflection point. It may or may not be an inflection point. Why? Well, inflection points occur where you have a change of concavity as you pass through it. You go from concave up to concave down when you move left to right, or you go from concave down to concave up when you move from left to right. We have to check to see if that is so. So what we will do is be strategic. We will pick a point left of 2 and right of 2 and substitute into the second derivative to see if we get a change of positive to negative or negative to positive. And if we do, we have an inflection point. The strategic part comes from the fact that at the same time, let us pick carefully, and we'll choose 0 for the point left of 2 and 4 for the point right of 2, because this will enable us to kill 2 birds with 1 stone. We will be able to find the relative extrema at this moment. So evaluating the second derivative, which is 6x minus 12, at 0, we find that value to be negative 12. The key is that it's negative. It's less than 0. So that means at x equals 0, we're concave down. More to the point, because the second derivative is negative, at x equals 0, we have a relative maximum. 2 birds, 1 stone. Let's evaluate the second derivative at 4 on the other side of 2. We find that we get 24 minus 12, which is 12. This is positive. Well, right of x equals 2, the curve is concave up. And because we have a stationary point at 4, and the second derivative evaluated at the stationary point is positive, we have a relative minimum. Now, from the knowledge that we have a change of concavity, as I look left and right of x equals 2, I have concave down versus concave up. We have a change of concavity at the inflection point. That means at x equals 2, we can now say it's not possible at anymore. It is an inflection point. Let's reminisce. Let's look at this function. What have we found out? Well, we have found out that at x equals 0, there is a relative maximum. Picture it in your mind. At x equals 4, there is a relative minimum. Picture it in your mind. And at x equals 2, there exists an inflection point where left of 2, the graph is concave down. Right of 2, the graph is concave up. Does that information jive or coincide with the fact that we have a relative maximum left of 2 and a relative minimum right of 2? Yes, it does. We see our inflection point where the graph changes from concave down to concave up. We see our relative maximum at 0 and our relative minimum at x equals 4. Let's look at a second example, asking exactly the same questions we asked a moment ago. Find the stationary points, the point of inflection, and a location of relative maximum and minimum. Again, we begin by taking the first derivative, so we use the product rule. Derivative of x times e to the 4x plus x times 4e to the 4x. Now we want to solve, so the first thing we do is we recognize that we have a common factor, e to the 4x. We factor it out. And e to the 4x, the range of these exponential functions is positive. So I have a positive number times another factor. So when I set this equal to 0, all I have to do is worry about the factor 1 plus 4x. When I solve, I get x is equal to negative 1/4. Since that value is in the domain of the function, we have a stationary point. What do we do next? Well, now we're looking for points of inflection, so we take a second derivative. My I is here. I'm going to differentiate this version of the first derivative. Differentiate e to the 4x, you get 4e to the 4x times g times 1 plus 4x. Then take f, e to the 4x, and multiply by the derivative of 1 plus 4x, 4. Do you see a common factor, much as I had a moment ago? So when I take this equation and set it to 0, I'll factor out that common factor, and in the parentheses I have 1 plus 4x plus a placeholder here for this term, plus 1. Now, 4 times e to the 4x is always positive. So when I set my second derivative equal to 0, I'm only worried about the factor 2 plus 4x. If I solve, I can make it easier on myself if I factor out a 2, and I can quickly see x is equal to negative 1/2. What do we know? Well, we don't have an inflection point yet. We have a possible inflection point. We have to look at points left and right of negative 1/2. Now, I have to think about this for a moment. I have a number line. I see negative 1/2 on it. Negative 1/2 itself is a possible point of inflection. So I pick a point left of it, negative 1, and I pick a point right of it, and again I'll choose the stationary point so that I can not only tell the concavity right of negative 1/2, but I can also tell the type of extrema that exists at negative 0.25. So I evaluate the second derivative at negative 0.25, and I find that I have a positive number times 1 plus, now 1/4 of 2 is 1/2. So I have 1 plus negative 1/2. And that value that I'm multiplying by is positive. So when I'm done, I can just say to myself, okay, for the stationary point, I know because the graph is concave up, I can see a U-shape. I must have a U-shape. I must have a relative minimum. Now, right of this possible point of inflection, I must have, in this box here, concave down. Let's see. We evaluate it at negative 1. 8 times e to the negative 4 is positive. 8 times e to any number is positive. And 1 minus 2 is negative. So my second derivative evaluated at negative 1 is less than 0. Concave down. Now I can say with abject certainty that at x is negative a half, I do have a point of inflection because I have a change of concavity. As I move from left to right, I go from concave down to concave up. Now, let's reminisce. Let's see if we can think for a moment. If this is the function, what do we know? Well, at x is negative a quarter, we have a stationary point. But moreover, we have a relative minimum there. And at x equals negative 0.5, we have the location of an inflection point. But moreover, left of negative a half, we're concave down. Right, we are concave up. Can you picture what the graph looks like? Well, you see the location of the inflection point in brown. This relative minima for negative 0.25 shows the extreme point where the graph is concave up. We have the U shape. So we're going from concave down to concave up when we go from left to right and pass through the inflection point. But notice one more attribute of the graph. Where the graph is concave up, we have this U shape that we so commonly see. Because we have an extrema, we do have a minimum. But where the graph is concave up, we're looking at just a portion of that upside down U. And we have asymptotic behavior as we move to the left. There is no second extreme point. We never do hit a highest point as we approach negative infinity. But what we do is get closer and closer to y equals 0. Thank you.